Good evening everyone. Our next topic in classical mechanics series is conservation theorem for angular momentum of a particle. It's angular. Dear student, our first topic was mechanics of a particle, and this topic is also covered under that topic, mechanics of a particle. Dear student, consider a particle of mass m which is moving arbitrarily in space with some velocity v. So students say it's a particle of mass m and it is moving with some velocity v. Then its linear momentum will be p equals mv. The direction of momentum and velocity is same, so we can say this is the direction for p. Dear student, as the particle is moving in two-dimensional space, here we can say it's a two-dimensional Euclidean space, and we can generalize it into three-dimensional space. Then we select a point O, which is our origin of this right-handed coordinate system. And student, the position vector of particle which is moving with the momentum p is, say, r. It is not necessary that we have to select O here. You can select your own coordinate system. Dear student, this is the position vector r. As the particle is moving, so we can say this r is a function of time. Then angular momentum is a quantity which is defined for this particle in this way. Angular momentum is lowercase l is the cross product of position vector of this particle and the linear momentum. This is lowercase l. You might have also encountered with angular momentum with uppercase L. That is for a system of particle, which is the topic which is we are going to discuss after, as we are going to finish this mechanics of a particle. Then we will go to the mechanics of a system of particle. Student, L is r cross p. R is the position vector, p is the linear momentum, r is the position vector from point O. We must have to mention this, that this L is about this point O, because if this O is different, if I have taken O at this point, then our L will be different. So I have to mention this point here about O. And dear student, we can also define one more dynamical variable for this particle, that is torque. Torque is the moment of force. It is the cross product of the position vector about this point O and the force which is acting on the particle. Dear student, L is also known as moment of linear momentum and tau is also known as moment of force. Again, we have to write it about this, about O. Dear student, let's differentiate this expression with respect to time. One most important point which we have to mention here is the order of cross product is important. We cannot say it's p cross r, it is r cross p, because the cross product of two vector is always anti-commutative. Now student, differentiating this expression with respect to time, I'll get dl by dt, that is the rate of change of angular momentum, is dy dt of r cross p. Now we have to apply the product rule of differentiation with preserving the order of r and p. Dear student, I will say the first function r as it is cross the differentiation of p with respect to time plus differentiation of the first function and the cross product with the second function. Dear student, it comes out to be R cross the force. Rate of change of linear momentum is force plus this is my velocity. Rate of change of displacement is velocity cross the linear momentum. Dear student, my left hand side is dl by dt. Rate of change of angular momentum is r cross f plus v cross mv. The first line which I have written, v cross v, they are in the same direction, so I'll get 0 because the cross product of two parallel vector or two identical vector is 0. Then I'll get dl by dt is r cross f plus 0. R cross f is my torque. Dear students, this we can say the rotational analog of our Newton's second law. Our Newton's second law was F is equal to dP by dt. This equation is equivalent to this equation. The only difference is that here linear motion is involved and here rotational motion is involved. So to change the linear state means to change the linear momentum. If you want to decrease linear momentum or increase linear momentum, or to change the direction, want to change the direction of linear momentum, you need a force. In the same way, if you want to change the rotational state of the object, rotational state means you want to increase the angular momentum or you want to decrease the angular momentum or you want to change the direction of angular momentum, you need a torque. Let me give a bit example. Say this is our scale, and dear student, if I would like to change the state of this scale, means linear state, I want to move it with some velocity v. It means I am applying some force over this. To change the linear momentum, you need a force. And dear student, if I have a ball and dear student, its angular momentum is 0, if I am rotating on its axis, I need a torque. Although this is not the example of a ball, this is a point and this is not a point. Yes, we can say if I am rotating it like this is a circular motion. This ball, I can consider that this is a point object and it is rotating in this way. Now I can say I am applying some torque over this. I cannot say it's the only force. It is force is also there, but in correct term we can say we have to apply some torque over this to change the angular state of this point object. Now student, again, if tau equals 0, then we can say dl by dt equals 0 or L is constant. If there is no any torque on the particle or the sum of various torques acting on the particle, the vector sum of all the torques acting on the particle is 0, then its angular momentum is going to be constant. Again, there is an arrow over this symbol. It means its magnitude as well as the direction is not going to change. So this was our law of conservation of angular momentum for a particle. Dear student, you may take the screenshot, and thanks for watching the video.